tested spent a few days at NASA Ames Research Center in Silicon Valley to explore a few of the labs, workshops, and testing environments used in the development of space exploration technology. One type of technology we definitely needed to check out were the robots.
We found one of the robots at the Roverscape, a large fenced-off area filled with rocks, craters, and small hills used to simulate the terrain of surfaces like the Moon or Mars. These aren't autonomous robots, but their pilots may be astronauts remotely controlling them from space. In 2013, 3 astronauts aboard the International Space Station tested out remotely operating a rover on this very Roverscape from orbit. The Intelligent Robotics Group brought out one of their rover testing platforms for us to check out, and I was pretty psyched to take it out for a test drive.
Look at robots.
Yes, awesome.
Hi, Arno. Hi. Good to see you.
Good to see you too.
So where are we right now?
So we are in one of our testing facility from the robotics group at NASA Ames Research Center. We call it the Roverscape because a lot of the tests that we are doing are rover focused. We are also testing some other robots such as UAVs and then some like fancy robot that we develop in-house.
So it sounds like there are 2 things we want to talk about. One, like the terrain and what the objectives are in designing this landscape, and also this robot itself. Is this supposed to represent just, it could be versatile, any different type of environment, not necessarily the Moon or Mars?
Yeah, so it hasn't a specific focus. We definitely use it for any terrain. So for us, usually our project are Mars or Moon focus, but sometimes we also focus on some moon of Jupiter or Saturn. There's different kind of environments with more or less fidelity that we call analog that would represent what we think we would find on the Moon or Mars.
So how close or not we are to actually being on the Moon or Mars right now.
Exactly.
We're not
this
exactly
is not,
on.
Right.
Yeah.
These plastic rocks are not exactly what you'd find.
Yeah.
Exactly. But the cool thing is that the robot has some sensors, and to some extent we can make those sensors believe those are real, and they're real enough for the robot at least. So that's why we usually start in this, like as I said, low fidelity environment to do some testing. And then afterwards we go to higher fidelity environments such as the Atacama Desert for one of our projects, or in the Canadian Arctic. And then there, this represents a higher fidelity environment, both for the robot and sometimes also for the scientists.
So what exactly can this rover do? Like what are the capabilities of what we can see today?
So if you think of a rover, what it really is a way to bring science to a specific point. And it has the advantage of being mobile. So if you were to go on the Moon, you could either land and be static and then observe what is surrounding basically your landing spot. But if you want to explore further, you need a mobile platform. And this is exactly what a rover is. In our case, we have 4 wheels that are all driven and all steered. So the rover can go over multiple types of terrain, uphill, downhill. We usually limit to slope about like 20 degrees, but in practice it can go probably to like 40, 45 degree slope, depending on the terrain. And then we can also go over obstacles. So on top of those 4 driven wheels, we have a suspension mechanism that we call a differential mechanical linkage that links the 2 rockers, but allows them to rotate individually to keep all 4 wheels in contact with the ground at all times. And this means that if I'm going over a rock that I can just demonstrate right now, you'll see that all the 4 points of contacts are going to be on the ground, while both rockers are going to move independently from each other. So I enable the robot. You can hear the click. That is the magnetic motor. And then I'm going to drive forward towards that rock and go with 1 wheel over it.
Oh, wow.
And you can see those like 2 clear, distinct angles in between the rockers. And this is this differential suspension mechanism working.
And so my understanding is this platform isn't supposed to represent any one single type of robot or rover that NASA's working on, but just the capabilities of kind of the stress that a mobile laboratory would need to endure.
That is correct. So we are not, as you said, like designing for a particular mission. We are designing a rover that can be used in multiple scenarios that can carry a certain amount of science, basically. So in our case, our payload is about 200 kilograms, but could be used on a lunar mission to do some testing or a Mars mission. So it's not specifically designed for one terrain in particular.
And how challenging is it to actually put together a prototype rover like this? You know, if someone at home wanted to make their own prototype rover, was this like a lot of work, or is this something you can kind of like put together?
So the very cool thing is that this is fairly challenging to put together because we have a lot of constraints working like for NASA and working with like very expensive equipment, needed to be very robust when we go testing, so very reliable system. But if you look at the overall system itself, it's fairly simple. So it's a few motors. In our case, like very high quality, expensive motors, but you can have like a simple servo motors costing a few dozens of dollars, being your replacement for your driving motor, and then the whole chassis being 3D printed or rapidly manufactured. And then on top of this, the control can be done, on like any Raspberry Pi or even potentially a microcontroller. So anybody in theory could like put their own rover together, and it's working out quite like a few things. So probably a lot of time that you need to invest, but it's not that difficult overall.
In the robotics group, and where you're working from, or the people usually have engineering backgrounds, like we're working kids who want to do what you do in the future. Where can they get started, and where would you recommend?
So the first thing is, I think, is being really passionate by science and engineering in general, and that's like the one quality that we always look for. And then obviously you need to gain some technical knowledge. So our group is really focused on usually computer science and then some mechanical engineering. So robotics needs like a whole broad set of skills, but eventually any technical person could help us out and design or work on part of that system.
Super cool. Thank you so much.
Yeah.
It's amazing.
But of course, the rover operators at NASA aren't going to be using commercial gamepads to control rovers on the moon. That's done with custom-made mission control software. And as we found out, software that's being developed at Ames, and it's an open source framework. We visited the Lunar Planning Lab to see how OpenMCT can be used to simulate the planning and operations of a future rover mission.
Okay, so what we're looking at here is some rover driving software. So this is software that we use kind of both in testing here at Ames Research Center. You might have seen as you came in, there's a rover yard where we test this with kind of real hardware. We also use it for running simulations, so simulating kind of potential future lunar rover missions. So the role of the driver who's using this software is basically to kind of navigate around using waypoints on the surface of the moon and kind of avoiding obstacles along the way, trying not to drive into craters and those kinds of things.
So you're going to show us how to drive on the moon?
Yeah, sure. So the way that we kind of drive a rover on the moon is the first thing to do is look around the rover and make an assessment of kind of where is safe to drive. So looking here, I've got some kind of pink spots and some kind of blank areas here where I don't have good data. But over here, I can see that there's some nice kind of green, safe terrain for me to drive on. So the first thing I'm going to do is turn the rover to the right. And then command it to drive. And you're going to see a delay while that happens. And that delay is a simulation of the communications delay when you're operating a rover on the moon. So it takes a couple of seconds just for light to get to the moon. And then you have some like kind of network delays and other things.
So it's a very iterative process where you go step by step, acquiring new data with each step. Is there a general best practice as to how many steps you want to operate and what not to tax and overload?
So that's something that we're actively trying to figure out right now. That's why we have these simulations. What we're simulating as much as anything is what we call the concept of operation. So we're kind of trying to figure out the best mode of operating a rover like this. Operating a rover on the moon is quite different to operating a rover on Mars. On Mars, you have much longer kind of light speed delays. So our delays of a few seconds, that probably seems quite kind of luxurious.
Yeah, this is snappy and fast.
Exactly, yeah. I'm sure the MSL operators would be very happy to have that problem. So in our case, we can have a much shorter decision cycle. But Yeah, in terms of how far we drive with each kind of waypoint, that's something that we're figuring out, and how much ground we can cover in a shift but these are all questions that we're trying to answer right now.
I know this looks slow and it looks methodical, but it's actually quite thrilling. I find. Like it's like you don't want to screw it up. I can only imagine a real operator operating a robot, off Earth. How nervous that might make you.
Yeah, exactly. And this is just a simulation, as you say, but it's the simulation is intended to be as kind of realistic as possible. So these images that are coming out of our simulator in terms of kind of the lighting environment and so on, it's intended to be as realistic as possible so that we can put our candidate drivers in as realistic a scenario as possible.
Cool. Thank you very much.
Yeah, no worries.
That's one big hangar.
Yeah.
Ariel, what is this?
So this is Hangar 1. I believe it's the largest hangar ever, I think. Hangar 1 used to hold big airships for the navies, and it was built in the 1930s. This used to have a skin all over it back when I worked at NASA Ames years ago, and they took it down, I think, because of asbestos or other toxic materials that they had to take out of it. So now it's a skeleton, but it's actually kind of hardcore and awesome as a skeleton, I think.
I like it as like a skeleton. So how long was it, when did it stop being in use? When they took the skin off, or?
I'm actually not sure. I think years ago they used to, I know that they had parties actually in Hangar 1 many years ago when it still had its skin on it. And then when they started taking all the skin off, that took several years, and then it kind of got decommissioned during that.
That's incredible. 1930s. The thing is, getting close to 100 years old, and even this, like, the architecture of it, it's kind of its time. It's really, really neat. And of course, in front of it, you got a little fleet of jets, NASA's fleet, because there's an airfield here, right?
Yeah, this is the Moffett Airfield. And I just love all the jets and everything because they've got the old NASA logos, which of course I prefer personally.